Okay, Taste of Industry, video 1, because there's probably going to be multiple. What I have open is the Word document with that I handed out when I gave these presentations. The softwares I'm going to use are open source. I'm not sure they work with Apple, but they do work on PC, and they are free. LT Spice, which comes from Linear Technologies, and Scilab, which comes from scilab.org. And I was asked to give a presentation on what industry wants, and so based on my experience and what I've seen over the years, they basically want employees that can solve problems. Yes, have soft skills, but with the skills to solve problems by testing a hypothesis, using proper test equipment the proper way. And so in community college and in the education system in general, how do people get there? How do students get there? And from a community college standpoint, what I would like to see coming in is students who know how to work with fractions. They know what a common denominator is. They've had enough experience that they just can do it. Know how to solve simultaneous equations. And I'm actually going to show you a shortcut today on that. Knows and can do problems in scientific notation, and knows about engineering notation, which is sometimes called metric prefixes. And knows how to use complex numbers in polar and rectangular forms. The complex numbers comes in when you go into AC circuits, because some components will shift the voltage and the current from each other, and the polar is used to basically define and understand that difference. As far as being a maintenance person on the floor or something like that, they're not going to use it a whole lot, but they sort of need that background as far as where it comes from. Knows enough trig to be able to convert between polar and rectangular forms, and I would also say this would also apply to something like power factor, which is a very important thing in an industry, managing power factor. And if they can do the math to do power factor, they can do the polar and rectangular forms of complex numbers. So what I did is I gave a simple circuit, and I'm going to build this circuit in Scilab, and then I'm going to solve it. Not in Scilab, but I'm going to build it in LT Spice. I'm going to talk through writing the equations and then solving them in Scilab. This circuit is going to give me 3 simultaneous equations, because there's basically 3 unknowns in this circuit. I don't know the current through this resistor, I don't know the current through this resistor, and I don't know the current through this resistor. All I've been given is the voltage source for the circuit, 24 volts, and the values of 3 resistors. This is not the most elementary circuit, but it's really the first ones you get to that you sort of have to do some calculation, you sort of have to do some analysis. So my voltage across my 3K and my 8K, I'm telling you up front, is 19.2 volts. The voltage across my 2K is 4.8 volts. And then I have these questions down here below. And is the circuit working properly? With these values, is this circuit working properly? Okay. Well, you got to be able to analyze the circuit to know, don't you? And that's sort of where we're going. That's sort of the skills we want to teach and get people to understand. If the circuit is not working properly, what should the values be? So if the circuit is properly built, properly wired, and there's no fault in it, what should the values be? I have to know those values to know whether these values up here that I gave you are correct or not. And then if the circuit is broken, usually in troubleshooting, you're looking for what we call a single point of failure. So you want to find the one component and the one condition. Usually it's an open or a short that would cause the values to go from what they should be to what I gave you. And then my last question is, can you know if it's broke if you don't know what the normal is? And the answer really is no. So unless everything you've got is documented as to what normal should be, then you can't really know what abnormal is. So you've got to have that skill, and that's a lot of the electrical skill in terms of troubleshooting is being able to analyze. Is this working the way it should work? Now I have Kirchhoff's laws for conventional flow, and I put them in there. The key to Kirchhoff's laws for circuit analysis and solving by hand is to be consistent. I'm a conventional flow type person, and there are electron flow people. They have their own rules, but the key is once you start going around the circuit, you are consistent. As previously stated, I have 3 unknown currents because I didn't give you any current values. So basically the current through the 3K, the current through the 8K, and the current through the 2K can all be different. One of Kirchhoff's laws says the currents entering a point, say this blue dot right here, or blue square, has to equal the current leaving. And if you're a conventional current sort of person, then you know that the current flowing through the 3K is probably going from left to right, and the current flowing through the 8K is probably going from left to right, and the current flowing through the 2K is probably going from left to right, because we're going basically from positive to negative. The electron folks would do it the opposite way, but they have an analysis. When you do come up with a current, whether you do it conventional or electron, you will get a number, and sometimes that number is negative. And a negative number just indicates the way you think the current's flowing is opposite the way it actually is, whether it's conventional or electron. So I'm pretty comfortable with the I3K, which is what I would name that variable, or an I3 for a 3K resistor, an I8 for an 8K resistor, and I2 for the 2K resistor. And based on the way I think the current's flowing, and you don't have to know which way the current's flowing, I3 plus I8 will equal I2. So I'm going to minimize this for a minute and go to a new document so I can type. Oh, we have to go bigger. Okay, I3 plus I2, I8, sorry, equals I2. And that is one of my 3 equations. Since I have 3 unknowns, I need 3 equations. So if I window back to this and make it large. The other equations involve writing loops, and Kirchhoff's voltage law says the sum of the voltage drops around any closed loop is 0. So if I go all the way around the outside, which is what I did when I demonstrated, then my voltage drops are the source voltage, the current through the 3K times the 3K resistance, the current through the 2K times the 2K resistance, and all those voltage drops have to add up to 0. So if I go in a clockwise fashion around here and I start with this current times this resistance, I get 3K or 3000 times I3 plus 2000 times I2, which would be this voltage drop. And then voltage drops for battery sources, you go by the terminal you come to first. So this would be a minus 24. So if I window back and I write those down, my second equation is 3000. I got rid of the K, I3, plus 2000, I2, minus 24 equals 0. So there's equation number 2. So I have 2 equations. I need one more. Well, I'm a little bit lazy, so I like to have two-term equations. So I'm going to loop around this little box here, and I'm going to go clockwise around the little box. And when I go clockwise around the little box, my current through the 3K is going in the same direction from left to right. But now my loop in the bottom part is going from right to left, while my current's going from left to right. Anytime the directions are backwards, it becomes negative. So my two terms in this one are I3000 I3 minus, due to the difference in directions, 8000 I8. And that is that equation. So 3000 I3 minus 8000 I8. And all those voltages have to add up to 0. Okay? So those are three equations that come from three circuit analysis laws. Now what I want to do is build what we call a coefficient matrix. So I'm going to start out with an I3 column, an I2 column, and an I8 column. And then what I like to do is put in my equals and my constants, because I do have a constant in these equations. I do have this 24, so it would be over here as a constant. So if I look at the coefficient of these equations and I put them into standard form, then this is a 1, this is a 1, and this is a minus 1. So from terms of coefficients, I have a 1. I2 would be negative 1. I8 would be positive 1, and my constant would be a 0. Going to the second equation, I'm looking at the coefficients. 3000, 2000. There is no I8 term, so its coefficient has to be 0. And then my constant is 24. And then for my third equation, my I3 term is 3000. My I2 term is 0 because there is no I2. My I8 term is minus 8000. And my constant is 0. So basically I just rearranged these equations into standard forms and pulled out the variables up to the top. So all I'm dealing with is the coefficients. Now, instead of solving simultaneous equations, I encourage people to use shortcuts. And one of the shortcuts that I like to use is something called Scilab. And I have to go pull it back up. There it is. So what we're going to do is we're going to use RREF, which is basically a matrix reduction function. And I'm going to open the parentheses, and I'm going to open a bracket, and then I'm going to go over here in my coefficient matrix that I just made, and I'm going to type it in. So my first row of coefficients is 1. You can use a comma or you can use a space. Minus 1, space, 1, space, 0, semicolon. When you get to the end of the row, you put a semicolon. So now I can start the second row. And pretty sure I can mix and match if I want to use commas. 24, semicolon, just showing you what you can do. 3000 space 0 space minus 8000 space 0. I'm at the end of the third row, so I don't put a semicolon. This is where I would close my bracket, close my parentheses, and hit my enter key. And what you see is that it reduces it. And my I3, one I3 is equal to this number. I2 and I8 are zeros. 1 I2 is equal to this number, and 1 I8 is equal to this number. So basically, with Scilab, I can solve it real quick. I3 equals 4.2 milli. I2 equals 5.7 milli. And I8 equals 1.6 milli. Okay, I'll pick up from here on my next video. Thanks for watching.